later things like in the bulk, maybe there's some signature there.
Oh, I see.
Yeah, just to get a clarification, you mentioned this bilayer honeycomb system in oxides.
Yes.
How does the charge gap depend on the end, the layers? Do you see that? Yeah, just you went very fast.
Okay. Yeah, actually, we haven't measured the opacity yet. Right? So this is 2-layer, 4-layer, 6-layer, and clearly, the gap is kind of increasing. But activation is not, that big, so that means the gap is very small. Yeah, so very narrow gap. Yeah. Actually, we see anomalous voltage. So therefore, at least there must be a ferromagnetic component. This could be weak ferromagnetism or canted ferromagnetism. We don't know actually what all these things. But these we have to do X-ray. At least this insulating state, we see ferro moment perpendicular to the plane. And in case of 001, pseudosphere lying in the plane. So now, it's been like a 90 degrees rotating.
So according to our calculation, the spin in the axis is along the 111 direction. So in some sense, it's consistent with the X.
But you use the anti-ferro.
Yeah.
But I'm saying a 111 direction ferro moment we observe.
Okay, then I have no idea. So maybe you have to include the tuning of the using both things. So this is a perovskite-derived structure. It's very different from 2 and 3 honeycomb.
Yes.
The honeycomb is not plain.
Yeah, so no type.
Yeah. And do you have any idea? Satoshi pointed out that there is a symmetry breaking due to the rotation, which can give DM interaction as a 214.
Yeah, that we thought about that. And it could be, but because X-ray is hard to see option, so we don't know yet. But if this moment is, due to weak, ferromagnetism, canted magnetism, there must be still stimulation, proportion of force.
So the percentage.
Very last session of the day. I know we're all hanging in there. And so this is work that I did with Liang Fu, and it's very nice to have be able to collaborate with Vidya and others. And so now I'm going to speak about some of the theory and other considerations that went into our proposing the model. That, as you can see, there's been very exciting work done when we put out this paper already. So another interesting aspect of our work other interesting experimental systems that our work touches on is also the field of interface superconductivity. And that is a phenomenon in which you have materials that by themselves do not exhibit superconductivity or superconduct at much lower temperatures. And when you put them together as the interface, they do exhibit superconductivity. One is, of course, a celebrated example of Aleo S2. There's been a lot of activity recently. And even more recently, there's been some very exciting new work in which certain materials, for example, single-layer iron selenide, are put on STO, and they've seen really astonishing results, a TC of over 100 Kelvin, and there's more results coming out. So, of course, all of this begs the question of why and what is happening, what is going on at the interface. It turns out also that these materials, that these topological crystalline insulators that Vidya spoke about, also are part of the story, much older actually, that these experiments were done decades ago. And in these materials, which you'll recognize, that telluride, tin telluride, when they built these super lattices, again, they also saw where single films are not conducting. When you put them together, you start to see that these multi-layers can superconduct with a TC of up to 6 Kelvin. And this work was subsequently repeated over these decades, and then they extended it to different families in which they had down to bilayer systems now with different materials always in the same family. And so then you can start to really identify what contributes to this interface superconductivity. Up? This is better. Yeah, no, let me know. Yeah. And so this, of course, begs the question of, of where does superconductivity emerge at the interface, and can we, describe or understand the origin of the mechanism behind this? And of course, as pointed out, that these materials that we're looking at today do fall into the class of topological crystalline insulators. Vidya gave a beautiful introduction to them, so I won't need to spend much more time on that. But what we really want to look at here is look at how a model of the effects of strain on these Dirac fermions at the surface of these materials give rise to pseudomagnetic field Landau levels, consequently a large density of states that then can contribute to an unusual superconductivity. And of course, we want to compare our theoretical model to the experiment and continue to give some other experimental predictions that could be used to verify a proposal, and then followed by wrapping up. So, of course, now you've already seen these pictures of this rock salt structure and this family of materials, or this 4-6 semiconductor material family class, in which you do have these surface states on different surfaces. And under different forms of mechanical or chemical pressure, then these materials, if they are not already topological, can undergo band inversion through these mechanisms to become topological, and they're protected by mirror symmetry and U1 charge conservation, as Vidya pointed out, in contrast to regular TIs, which is time reverse minus U1. And then of course, beautiful work done with Vidya to characterize the surface states in this material, and in particular, we will be focusing today on the 001 direction, because as I'm going to explain, that is where we see the strongest difference of these surface states with regular TIs, because there we actually see surface states that are tunable. And this is tunability that we're going to exploit to look at the effects of strain on this surface. So then this is data by Sahid and Vidya, just to note how there's these two, they come in pairs and they lie along two orthogonal mirror axes, distributed by 4-fold rotation symmetry. So this is a nice picture from the Higgs group, in which it illustrates very nicely the differences between regular TIs and TCIs, just so that we can get a feel for what we can expect in these materials. The Dirac points in regular TIs occur in odd numbers, and they are pinned at the high symmetry points. And so under time reversal, it goes back into itself, and hence under something like strain, there is going to be no effect. Whereas in these TCIs, they are not constrained to lie along the high symmetry points, and as we saw, that they can be tuned along this mirror axis. And this is a tunability, and since they always occur in pairs, which means that under a field such as strain, they can move oppositely, such that overall it does not bring time reversal symmetry, but they can move in opposite directions. along this mirror axis in a continuous fashion. And again, this tunability is going to be what is going to give rise to the kinds of effects that we can see here. So the video already showed this data, and this is showing how through a different mechanism, changing the alloy composition of this material, that one can shift the position of these Dirac cones closer and closer towards the zone boundary, so that at the transition point, because it transitions from a topological material to a trivial material, then they disappear. And this is alloy composition, but we get a similar effect from strain. So then to see what strain does, we can simply look at the symmetry analysis to understand its effects. And if we do preserve all fourfold symmetry, then we naturally expect that strain pushes the Dirac cone in an equal manner towards or away from the zone center, and continues to preserve the fourfold rotation symmetry. And if we break down the fourfold rotation to twofold rotation, then naturally we do expect the Dirac cones, to have a pair shifting towards the zone center and a pair shifting away from the zone center. And if in this case we break the mirror symmetry, such as with shear strain, then naturally we do expect the Dirac cones to move away from the mirror axes in such a fashion. And so this is the way in which we can parameterize the different kinds of strain that we can apply to this system, and hence alter this. And this video pointed out that the movement of these Dirac cones is similar to graphene. However, because of the crystal symmetry in these materials that is different from graphene, in graphene there is only one way in which strain can rotate these Dirac cones, whereas here we have three independent ways in which we can manipulate the Dirac cones in these materials. This symmetry analysis was supported by ab initio calculations, in which here they did calculate how different types of strain will alter and change can cause firstly a phase transition into the topological phase, and then subsequently push away the Dirac cones away from the zone boundary. So we see here with three different materials that at a certain onset of strain, then we start to see the Dirac cones appearing. This characterizes how far away they are, and they do move away. So this is consistent with our symmetry analysis. And because of the nice linearity of the Dirac fermions, we can make